Okay, so today I want to discuss a bit more the technical part of the proof, which consists in studying the volume functions that I defined yesterday. I will revise them today, and to doing asymptotic expansions and to showing the main goal is to show that the coefficients in this asymptotic expansion have a special property which Joel Friedman called Ramanujan property. So let me start with a definition of local topological type. Of a closed curve in a surface. So local topological types is going to be formed by a pair, which is a surface with boundaries of genus G0 and N0 boundary component, and some closed curve contained in the surface. And we will assume that it fills this surface. So this is a common terminology for people who do who study curves in surfaces. So yeah, maybe one. So yesterday I drew two examples. So one example is a pair of points with figure 8. We could also consider pair of points with this curve, for instance. Or, I mean, yeah, these are two possible examples. And filling, so the fact that the curve fills the surface means that if I consider the complement of the curve in the surface, the connected components are either disks or are either contractible or they are cylinders near the boundary. So, So the complement of the curve in the surface is made either of disks or of peripheral cylinders. So in these examples, for instance, if you remove the curve from the surface, you get 3 cylinders. In this example, one of the components is a disk, and this is allowed. But this is the only two kinds of components that are allowed. And yesterday we said that there is a proposition which says that if I integrate over the moduli, I'll integrate over the moduli space of hyperbolic surfaces of genus G a certain special kind of test function. So I want to, so F compactly supported. And I'm going to integrate a certain special form of random variables, which is the sum over all periodic geodesic having the topological type T of F of the length of gamma. And I'm going to integrate with respect to the Weil-Petersson measure. And the proposition for the moment just says that there is a density. So this integral is of the form integral of F of L times some density. So if we were considering simple curves, this would be Mirzakhani's volume polynomials, but more generally, and this is not really hard to see, if you fix a topological type, you always have a density. The theorem is that so first part of the theorem is that if I divide by the total volume of the moduli space, this quantity has an asymptotic expansion. So to any order into inverse. So we are talking about the limit where the genus go to infinity. So I'm drawing asymptotic expansions in inverse powers of the genus, and there is some remainder term, which is typically is going to be like O of L over G to the C plus 1, something like that. And in fact, what you can show, I mean, it follows from previous work. Actually, the asymptotic expansion starts exactly at the Euler characteristic of this surface. So it starts at chi0, where chi0 is the opposite of the Euler characteristic. So it's minus the Euler characteristic. So in particular, the only curves that give contributions of order 1 are the simple curves. As soon as you consider curves with self-intersections, the asymptotic expansion will start at a higher order. And the higher, the larger the Euler characteristic of the surface is, you get higher orders for higher Euler characteristics. And so this is the first part of the theorem, and the most important part is to show that these functions is a Ramanujan function. Each of these functions is a Ramanujan function.
Remind me what VG was?
VG is the Weil-Petersson measure a priori is not normalized. So it's the total measure of the moduli space. And you divide by VG because actually you want, here for the moment. So you have to, if you want to have a probability measure, you just divide by the total volume. So what is the definition of a Ramanujan function? It comes from Joel Friedman's paper for graphs. So you have a function defined on R plus.
Could I ask a stupid question? I was not able to attend yesterday. I'm very sorry. But type is up to homotopy, or it has to be exactly that pattern of intersection?
It's modulo some equivalence relation. In particular, homotopy. You have to be able to homotope. There is a So you're going to say that two such things are equivalent if there is a diffeomorphism from one surface to the other, sending the curve to a curve in the same homotopy class. And so the reason why you don't say just diffeomorphism is this kind of pictures.
You can turn triangles upside down?
Yeah, exactly. This problem of triangles that you want. So you want this picture to be the same, to be the same topological type as as this one. Okay.
Yeah, thank you.
You want to be able to do Reidemeister moves because when we consider closed geodesics, we just fit the homotopy class and we cannot do more. So this is the same topological type as this. So we say that the function is a Ramanujan function. I think we impose that it's continuous, just we assume a priori that it's continuous. But we don't want to assume more regularity. We say it's a Ramanujan function if it's of the form some polynomial of L times exponential L plus big O of L to some power. And of course, we can put, once we have fixed the degree of the polynomial and we have fixed C, we can put some semi-norms, etc. In the paper, we need to control, actually, we need to control the norms of the functions that we get, but I'm not going to go too much into these details. And one important property is the stability under convolutions. So if you have F1 and F2 that are Ramanujan functions, you define the convolution in the usual way. So it's the integral from 0 to L of F1 of t, F2 of L minus t dt. And it's still is also Ramanujan. You can try to do it as an exercise. It's not very hard, but at some point you have to do a slightly clever thing. Like you have to, well, it's when you do the off-diagonal calculation that there is some slightly clever thing to do, but it's not very hard. And
in this C, I mean, it's sort of just any constant, because there's all sorts of parameters that are going. I mean, G and L are both going to infinity, and
yes.
somehow K.
No, C is fixed. Yeah.
Also the degree.
The degree is fixed, C is fixed. But in our proof, it's important to control the degrees that will appear. So in particular, yeah. For every m, we have this notation for the class of Ramanujan functions such that p is of degree less than m minus 1, and the remainder is of degree c.
So when you add on all these simple topological types, and is there going to be a cancellation in the p's? You mentioned that Joel had some inclusion exclusion. Is it going to be important what the coefficients of the p are?
No, that's really the main point in the proof, is that you never need to compute those
That's
coefficients.
because it's a term times e to the L.
It's because of this.
There's nothing between e to the L and e to the L over 2.
But so remark, in our paper where we prove the lambda 1 is at least 2/9, we actually showed, so sorry, this is a 9, it's not a G. We saw yesterday that if you want to prove 2/9, it's enough to show that F1t is Ramanujan. And for F1t, if you sweat hard enough, you can actually compute it by hand. This is what we do. So it can be. But of course, for the next ones, you really don't want to compute them. And really the main point of the proof is that it's enough to show that they are Ramanujan. You don't need to compute them, because this integration by parts is going to kill anyway. It's going to kill all these polynomials.
So you're killing the.
So even, and that's very good, because when you do this integration formula, sometimes you need to divide by the stabilizer of the curve. So it's very easy to make combinatorial mistakes. It's like some curves like for instance, this figure 8 has more symmetries than this one. So it's very easy to make combinatorial mistakes. And the good point is that even if we make such mistakes, the proof is very robust to this kind of mistake. So maybe I can say already where convolutions appear in Joel Friedman's proof. So for graphs, you really can apply this convolution property for regular graph. Because if you have a, so for Joel Friedman, a topological type is just a picture like that. There is no two-dimensional object, it's just some picture. Or another one is going to be, for instance, like that. So once you have a picture like that, you can assign length to each. So this means that you have decomposed your geodesic into simple pieces. So this is equal to this plus 2 times this one plus this. So you have decomposed, so this homotopy class in this picture has been decomposed into 2 simple curves and twice a segment joining the simple curve. And now, in the case of graphs, you assign length to all parts. And so Friedman is able to show, and the calculation for graphs is, I mean, it's clever, but it's elementary. You can show that the contribution to the volume function of each of a simple curve is a Ramanujan function. And now you use the fact that the length of this curve is the sum of the lengths to see that the volume function is a convolution of Ramanujan function. So it's really, for graphs, it's really the fact that the length of this curve is the sum of the lengths that allows you to really write a convolution at the end. So we will try to apply a similar idea. Unfortunately, we are not in a curvature -1. We are on a hyperbolic surface. So if we have a curve like that, we are going at some point in the proof to decompose it into 2 simple curves and an orthogeodesic, but the length of the geodesic in the homotopy class is not going to be the sum of the length, so it's going to introduce some complications, but this is the rough idea behind that.
Just a very stupid question. What does this picture here stand for? And it's sort of which order you go to, or is it not important which order you go to?
Well, if you read Friedman's paper, that's one part which is complicated to read, but you start with a homotopy class, which, so originally the maximal information that you have is really not only the length of each part, but which order you go through. Mm-hmm. In his paper, I think it's a matter of taste. In his paper, at the end, he just considered this picture where you forget about all information, you even forget in which order you go through. I prefer to remember in which order we go through the different parts. But it's mostly a matter of taste. So you at some point, you group all the curves according to, you group them into classes that look similar.
But in the explanation you gave before about convolution, you do care about the order.
Yes.
Right?
Yeah. Okay, so maybe now I should write more precisely what is this volume function. At some point you have to write some formula to say how to compute it.
In the Friedman case, the Mirzakhani formula is just elementary.
In Friedman's case, these guys they are basically binomial coefficients. And now when you divide by the total volume, you get a rational function. And this is actually what is used in the new proof. Yeah. It's rather elementary in the graph case, but okay, what is Okay, so it's an integral over some big space. So let's say we consider, for instance, this topological type. And now we are going to have some big surface of genus G. And we have to integrate over all the hyperbolic metrics on the big surface for which this curve is going to have length equal to L. So there is one integral which is over the moduli space of the complement of the surface. So this is the surface of genus 0 and G0 and N0. So there is one integral which is on the Teichmüller space of this surface and one integral which is on the moduli space of the. So we are going to
How do you distinguish one's Teichmüller, one's modular?
yes, because like the function that you're considering, it's invariant under the mapping class. It's invariant under the mapping class group of the complement, but not under the mapping class group of the interior. So, but it's quite painful to be. You have to be careful that some integrals are not on the Teichmüller space and some of them are on modular space. So these guys xi are going to be the boundary. So the xi are going to be the length of the boundary of this surface. Then we integrate over. We'll integrate over the moduli over all hyperbolic metrics inside the surface. So this one is on the Teichmüller spot. So this integral here is going to be on the Teichmüller space of a surface of genus G0 and N0 boundary component with boundary component set equal to x1, xn0. And Y is a hyperbolic metric on SG0. So Y is yeah. So this integral is on the Teichmüller space, and there is some function that I'm going to write in the next blackboard, which is a how do I write it? This one. So this one doesn't depend on the outside; it depends only on the inside of the small surface, and the other one is some function which is just a function of G of x1, xn0, and I'm going to write more precisely what it is on the next blackboard, but this is the volume of the moduli space of the complement of SG. So SG. So we take the complement of the small surface in the big surface, and we take the volume of the set of all hyperbolic metrics. So here xi are positive numbers, and y is in the Teichmüller space. Yeah, y is in the Teichmüller space of surfaces having boundary with fixed boundary lengths x1, xn0.
But to be clear, the measure is just the product measure on the x's, but the volume
Yes.
is built in the phi. Okay.
Yeah. And here, if you want to know, so this is an integral on a space of dimension 3 times the Euler characteristic of the surface. So here the number of parameters is fixed. What is depending on G is here, because it's the volume of the outside. This is just some fixed measure. And you have to, if we divide by the total volume, we get 1 over Vg.
So it's the integrand that's blowing up.
Hmm?
It's the integrand that's
Is this
complicated.
one which depends on G and which we have, so it's really this one for which we have to understand the asymptotic behavior when G goes to infinity. And this phi is a polynomial. It's a so phi G.
So G0 somehow is fixed, it doesn't go with everything else?
Yeah, because we have fixed the topological type. So yeah, G0 is fixed, N0 is fixed, the dependence on G is here. So phi G of
So but
X1.
for a fixed G, this is also, there are also several options for a fixed G, right? For the topological structure of the SG minus SG0.
Yes, so this one is a sum over all mapping class group orbits, which is the sum over all possible ways of all possible topological ways of putting. You have to sum over all possible ways of putting this small surface in the big one. So there is a sum over. So yeah, it's a sum over mapping class group orbits of, like in this example, one pair of points into a bit surface. And for each of them, so I'm not really saying here what I put, but for each of them, you get one of Mirzakhani's volume polynomial. So this is Mirzakhani volume polynomial.
Those are the ones from her early work when she generalized McShane.
No, here you don't use McShane. No, the McShane is used to obtain a recursion formulas on those. But here, I mean, this is actually quite simple. It's just saying that because your function, if you want to prove that they are polynomials, there are two ways. Either you use the Standard-Friedman, or you write the topological recursion using McShane, and then you prove by induction that they are polynomial. Okay. Just to make sure I don't forget anything. Okay. And so there is a theorem which is a combination of Mirzakhani isograph, and my first paper with Laura Monk, which is to show that phi G and actually here you should multiply by x1, xn0 because you have also the twist parameters. So this here count for the twist parameters around the boundary curves. So the theorem says that this thing has an asymptotic expansion. Which starts, as I've said, it starts at the Euler characteristic of the surface. Yes. So the existence of the asymptotic expansion is mostly proved in the Mirzakhani isograph, and our contribution is to understand these coefficients. So what we show is that these coefficients they have very special forms. So in each, there are linear combinations of functions which are either in each variable, they are either polynomials.
When you say asymptotic expansion, the x's are going up to infinity. So there's a statement about, I assume it's not for a fixed x, it's like x in some set. And what's the statement?
It says that if you stop at k, you can actually bound very precisely the remainder term. So it's the nature of the remainder term which tells you up to which k you. So I think it's like an infinity norm of x to some power divided by g to the k plus 1, and then there is exponential x1 plus xn0. Yeah, maybe just like that. So this tells, and in our proof of lambda1, x is going to be always of order log g. So we are very safe here. We could even go further than that. So these asymptotic expansions, they are like x can be quite large with respect to g. And the coefficients, there are linear combinations of functions which are in each variable, they are either polynomial. So for some variables, they are polynomial. For some other variable, they are the form cosh xi over 2 times the polynomial function. And for other variable, they are also like polynomial times sinh xi over 2. And we don't really need to compute there are some coefficients here, but we don't really try to compute them. And because the function needs to be odd, we know, I mean, there are some constraints on the parity of these guys, but we don't really care. What we know is that the sum of the degrees of over these two guys is bounded by 2k. So we have control on the degrees.
What is the technique of Zogroff and Mirzakhani do?
So it's always based on the recursion relation. It's a bit like when you do semi-classics, you have a Schrödinger equation, you want to, or a heat equation, you want to do asymptotic expansions, you just plug in your asymptotic expansion in the equation and you get conditions on the coefficients. And looking more closely at those conditions, we in fact obtain a precise form of the coefficients. Okay, and in fact, maybe we just concentrate on the leading order term, which was already computed by Mirzakhani and Petri. So corresponding to k equals the Euler characteristic. It's known that the leading order term it has a especially simple form, so it's a function of x1, x and 0. It's just the product of sine of xi over 2. So the first term is simpler than the other one. I also realized here I forgot to write something important. We are not integrating over the whole space, we are integrating on a slice where we impose that the length of the curve C should be equal to L. So we actually integrating on a hypersurface given by this condition. And here we actually taking this integration of the measure on this hypersurface, so which I denote by divided by DL. So this is really the interpretation of VGT of L. So in the Teichmüller space, we have one equation which defines a hypersurface, and this equation is just that we impose the length of the curve to be equal to L. And we integrate on this slice, we integrate this integration of the Weil-Petersson measure. So I think from now on, I'm just going to consider on this term. The other terms are a bit more complicated because they have these polynomial factors that are cause for complications, but not super interesting. Okay, now another important remark is the length comparison estimates. Okay, maybe. So I should say, so of course, to show that the volume function has an asymptotic expansion, of course, we use the fact that this guy under the integral has an asymptotic expansion. So we replace this guy by, so that it is plus, we replace this guy by its asymptotic expansion. So, yeah, I guess I cannot write to the bottom. But maybe, okay, if I want now to.
But now, once you put that in, and those you're starting to get your gamma functions, it looks like. You're getting an integral from 0 to infinity, multiple integral. Exponentials against powers, no?
I don't see how it would be a gamma function in the genus.
No, just a simple one.
Ah, okay.
I don't know. Well, I guess you.
Yeah, maybe. I don't know. I just started thinking about this question a few days ago, so I don't have very. But maybe I should say that now, if I want an expression of the coefficient phi fkt.
I'll make a prediction. You'll come back in 6 months and you'll say, it is a Selberg integral.
Okay. So to get the coefficients in the asymptotic expansion of this, we just replace this function by its asymptotic expansion, and we get that the quantity fkt of L is more or less the same integral, but where here instead of phi g we put fk g0 and 0 of x1 x and 0, and then we integrate over. So it's the same. So the expression of the coefficient for the topological type T is just obtained by replacing phi g by this coefficient here. And this coefficient now is we know explicitly what it looks like, and so we need to understand these integrals. Yeah, maybe I should just write. So if I'm just interested in a leading order term, it's going to look like integral of this product over the set of all Riemannian metric of all hyperbolic metrics such that the length of C for the metric Y is equal to L, integrated with respect to the Weil-Petersson measure. of a slice. So you see now, now there is no G anymore. This is really something which has some fixed measure on a fixed set and a well-identified function. The G has disappeared. And the dependence on the curve is really, the only thing that depends on the curve is that we are integrating on a slice which is defined by the curve. So back to what I was saying, the comparison estimates.
I mean, it's quite similar to Meta and Bourdon in random matrix theory when they compute the spacing. You have an n-dimensional integral, and you use orthogonal polynomials to convert that to an integrand which depends on n. You want to compute some correlation, and then you then you have to do semi-classic asymptotics on the n, like you're doing, and you get the main term, and then so you switch the number of variables for the integrand. That's what this formula that's useful. Very simple. This is much harder.
So comparison. So there is some simple inequalities that if you have a curve C that fills a surface, a given surface of genus G0 and N0 boundary component, then for every hyperbolic metric on S, so Y again is now is in the Teichmüller space of hyperbolic metrics such that the boundary components have lengths x1, n0. So there is so it's a simple lemma that if C fills the surface, then for every hyperbolic metric, the sum of boundary lengths is always going to be less than 2 times the length of the curve. And this is just by the variational property of geodesic. Like in my picture, if I have a pair of pants and I have, for instance, a figure 8, and here if this geodesic here have length x1, x2, x3, then this curve here is smaller than this one because it's the geodesic minima in the length in the homotopy class. This curve here is smaller than this one, and this curve here is smaller than the total. So if I do x1, so for this example, it would mean that x1 plus x2 plus x3 is less than 2 times the length of the curve. And this is very elementary. And already, if you do that, you get some a priori estimate on your integral because, so this is more or less like exponential sum of xi over 2. And so you can show that this is the whole integral is going to be, so this over 2 is going to kill this one. So the whole integral is going to be less than exponential L, which is the length of the curve. And there is a polynomial appearing just coming from the twist parameters. So there is some polynomial upper bound, which comes from the twist parameters. But just you have an a priori estimate, which is already of the right order. The point is that, and most of the previous work relied on this. The point is that if you want to do this integration by part, it's not enough to rely on an inequality. We really want to be able to estimate derivatives. So this is not what we want. We want exactly that it's a polynomial times exponential I plus a remainder term of a strictly lower order. But already, just this trivial inequality gives us the right order of magnitude. And in fact, this is the worst possible case, but there are curves for which you can actually improve this. There are curves for which you can improve the inequality. Okay, so this needs a definition. If I will define a maximal simple portion of C. So C is the curve, the simple curve, the closed curve. Okay, I'm not sure I will write the whole sentence, but a simple portion means a subset of the curve that has no self-intersection. And maximal means maximal for inclusion. So for instance, on this picture, this curve here, it's made of two maximal simple portions. It can be decomposed into this one and this one. Or if I have this curve here, it has three maximal simple portions.
Four.
Maybe four. Yeah, four. So this, and this. And we will say that a maximal simple portion so I'm going to write a maybe complicated sentence for something which is actually very simple. So a maximal simple portion is shielded. Then I will draw a picture, and I think the picture will be better than the sentence. It's shielded if it lies in the boundary of a contractible component of the complement of the curve in the surface. So for instance, let's look at this example. We saw earlier that if you take the complement of the curve in the surface, there is one component which is contractible. And so the one that we call shielded, I don't know if I have some red. The simple portions that we call shielded are this one, and this one. This one is not shielded. And the reason for this definition is that actually this inequality is not always optimal, and what we can say is that the sum of xi, so if again x1, x2, x3 is actually less. This is just by a variational property of geodesics. It's actually less than the length of the curve plus the length of unshielded portions. So for instance, for this curve, we could actually improve this inequality by saying that x1 plus x2 plus x3 is less than the length of the curve plus x1, which is better than this. And in particular, for many curves.
Don't you ever have a double shielded? You have from both sides.
double shielded. No, we have double filling. So if, in particular, if all the simple portions are shielded, we gain the factor 2 here. So there are some curves for which we gain the factor 2 here.
But the portion cannot be shielded from both sides?
It doesn't change the.
Okay.
I mean,
No.
maybe, I don't know. Yeah, everything we want to gain is a factor 2. Maybe if we wanted to gain, if we were interested in gaining a factor 3, we would have to do that. But because we're just interested in gaining a factor 2, we don't need to push the analysis to what you're saying. So definition, C is doubly filling. If all the maximal simple portions are shielded. So an example is this one. So it's a proper way of saying, so here you would like to say, like for instance, you would like to say the curve goes at least twice around every boundary component in some sense. This is a proper way of writing it. So for this, so in this case, we actually have that the sum of boundary components is less than the length of the curve. So we have, for this kind of curves, we have gained the factor 2. So in the case of doubly filling curves, actually we trivially gain the factor 2 here, and there is actually nothing to do. So what this shows is that actually the more complicated the curve gets, the less we have to work to prove the estimate. So the worst curves are those which have no shielded simple portions. In other words, are those for which the complement doesn't contain any disk. And we call them, in the paper, we call them generalized 8. Because they look like a figure 8, but with many loops. Like they look like that, or yes, they look like that. So basically, those are the curves for which we have to work the most. So I'm going to concentrate on those. I have no idea of the time. Okay, still
7 minutes.
7 minutes.
Can you explain that again? Why are these the only ones that you get here?
No, they are the ones, so for instance, for the 2/9, for the 2/9 paper, because we only need to do the asymptotic expansion to order 1. It's enough to consider curves that are in a pair of points. And for most curves, there is nothing to do, because for most curves, so the only curves for which we have to work are those which look like that. So they do just one loop on one side, and on the other side maybe. So for the 2/9, we only need to consider those. And what I'm saying is that this curve, so the worst case is actually really the figure 8 for the 2/9. As soon as you start winding around, you improve this inequality, and you need to work less. And if you do like, as soon as you do 2 loops here and 2 loops here, you don't need to work. So yeah. It does, unfortunately, it doesn't solve the problem of tangles. because you still need to sum all the estimates that you get on the other ones, and there's still a problem. But at least it shows that for the proof of the Ramanujan property, the more complicated the curve, the better life is for you. So now the question is how to calculate this integral. In particular, we need to express the Weil-Petersson measure. And here we are working in, we have introduced some new coordinates on the Teichmüller space. So suppose we want to study, for instance, this curve. We are going to choose a representative of the homotopy class, which will be of this type. So every generalized A can be coded by such a picture. So the picture is obtained by opening the intersections. It doesn't really matter if you open one way or the other. So when you open the intersections, you get simple curves. And then the intersections are coded by orthogeodesics. So we choose a representative of the homotopy class, which is obtained by going through this picture like this. And traditionally, on the Teichmüller space, people always consider function Nielsen coordinates because Wolpert showed that in the function Nielsen coordinates, the Weil-Petersson measure is just the Lebel measure. But for our problem, fixing some function Nielsen coordinates is not really helpful. Instead, the coordinates that we consider, so here the number of coordinates that we need is 3 times the Euler characteristic, or the absolute value of the. So for instance, on this picture, we would need 6 coordinates. And here the coordinates would be this length, θ1, here these 2 lengths, θ2, θ3, this one, and these the length of the 2 orthogeodesics. So these are the coordinates that we choose. And we can show, I think it's still something that I would like to investigate, but actually the measure that appears here has a particular, so the Weil-Petersson measure has a particularly nice expression in those coordinates. And I'm not sure I fully understand why, but that's the fact that. So the product of sine xi over 2 times the Weil-Petersson measure, in those coordinates, it's exactly, so here I'm going maybe to write the expression in this, just for this example, but it's similar for every such picture. It's going to be sine square θ1 over 2 sine square θ4 over 2 sine square θ2 plus θ3 over 2. And then there is sine T1, sine T2, and then times the Lebel measure. So you get the Lebel measure and multiply by something which is completely explicit and which looks pretty, it looks pretty much like exponential sum of theta I plus sum of Ti. So in those coordinates, we have a nice expression for the measure. And in particular, those guys, they are Ramanujan functions.
Two.
Okay.
I've got two.
And for the lead, so here I'm just discussing the leading order term, if you remember. So for the leading order term, the polynomial is just constant. For the other terms, it gets more complicated. But for the leading order term, we just have a constant function times an exponential function. So they are all. So here we're starting to see some convolution happening, and the true convolution would be if the length of C. So the length of C, if you look at the picture, is very close to the sum of theta I plus 2 times the sum of Ti. This is what would happen in the case of graphs. And in the case of graphs, basically this is the proof, like we have a sum and we have some Ramanujan functions, so we are really doing a convolutions. Here, what is complicated is that there are error terms. And maybe given the time, I'm not going to describe them, but you can, thanks to this picture, actually, we can exactly write, we have an exact expression of the length of the curve in those coordinates. So if you look at Mirzakhani's work, for instance, she already had noticed that the length of the curve was very close to being linear, but she always wrote inequalities. And here we don't want just inequalities because we want to estimate derivatives. But actually, this picture leads really we have an exact expression. And in the exact expression, we are really able to say how far we are from being linear. So I guess, yeah, maybe I'm not going to describe this part of the proof, but we don't use directly that Ramanujan functions are stable by convolution, but we show, we say it's like a pseudo convolution, because here the function is not exactly a sum, but we are able to control all the errors. So this part gets like quite technical, but it's just some analysis of what happens when you take a convolution, but instead of a sum, you have almost a sum, and you can control everything. And maybe it's good to stop here.
So, how many papers did you say are involved?
5. So there is the first paper that we wrote is the asymptotic expansion of the volume polynomials, so the calculation of the coefficients. So this is published. There is the one where we do the 2/9, and so the 2/9 is the same proof. It's just the fact that for the first coefficient, instead of using this general idea of convolutions, you just compute it by hand. And then, so I think we would like it to be a kind of pair with the one where we do 1/4, because large parts of the proof are similar. It's just that in general, instead of doing a calculation by hand, we use this convolution argument. On the other hand, we were told that if we can do 1/4, what would we want to publish a paper saying 2/9? But we still want to resubmit it. Maybe it was refused last year. But anyway, we think it's nice already to see that for the first coefficient, if you want, you can compute it by hand.
If something, the idea is clear and something published in some form.
Yes, but anyway. And there is one paper which is about the Möbius inversion formula. Like in Friedman's paper, the Möbius inversion, it takes like 3 lines. I think he could have expanded these lines to like 15 lines. I think it would have saved me. No, I think it would have saved me maybe 1 year if he had just. But for graphs, the Möbius inversion is a bit simpler because it's the whole story of the whole story of topological types is a bit simpler for graphs. So the whole discussion of the inclusion exclusion is slightly simpler for graphs. So we decided to write a separate paper explaining how to do the Möbius inversion. Also because in Friedman's paper it's really hidden in the middle, whereas it's an important idea. And there is one paper which is just like big. So it's the one which is already on archive, where I just give all the steps of the proof, but without giving all the technical details.
That's speaker.